These stars would radiate no light, possess no solid surface, and leave no typical electromagnetic footprint. Instead, they would act purely through gravity, subtly tugging on nearby stars, warping light from background sources, and influencing the rotational curves of galaxies in ways indistinguishable from the effects currently attributed to dark matter halos. What makes boson stars particularly intriguing is their capacity to mimic massive astrophysical objects while remaining fundamentally different in nature. Their formation could arise in the early universe from primordial field fluctuations, leading to solitonic cores within galactic centers or diffuse halos that contribute to the large-scale structure of the cosmos. Depending on the mass of the constituent bosons and the self-interaction strength, these stars could range in mass from stellar scales to millions of solar masses, potentially acting as seeds for galaxy formation or serving as alternatives to black holes in certain astrophysical environments. Because they are transparent to light and radiation, boson stars could easily evade traditional detection methods. However, their gravitational influence is not so easily hidden. If a star were to pass near a boson star, its trajectory would shift ever so slightly, a phenomenon detectable through precise astrometric measurements. Furthermore, gravitational lensing events, particularly those with unusual magnification patterns or extended durations, could hint at the presence of compact, non-luminous objects that match the predicted profiles of boson stars. As observational techniques improve and our understanding of scalar field dynamics deepens, the prospect of confirming or ruling out boson stars as components of dark matter becomes increasingly tangible. Their discovery would not only illuminate one of the deepest mysteries in cosmology but also open a new chapter in fundamental physics, revealing that the fabric of reality may be woven from the gentle oscillations of fields rather than the collisions of particles. If boson stars truly exist, their very nature challenges the boundaries between particle physics and cosmology. Their structure is governed not by degeneracy pressure or thermal gradients, but by the delicate balance between quantum field coherence and gravitational attraction. The scalar fields that compose such stars are described by solutions to the Klein-Gordon equation coupled to Einstein's field equations, yielding a non-trivial, self-gravitating solitonic configuration. Unlike fermions, which obey Fermi-Dirac statistics and are limited by the Pauli exclusion principle, bosons can occupy the same quantum state, allowing immense numbers of them to condense into a single macroscopic quantum object. A key feature is that the mass-radius relation of boson stars depends critically on the boson mass. For an ultralight boson with mass on the order of 10⁻22 10^-22 10⁻22 eV, a boson star could have a mass and size comparable to that of a galactic core. In contrast, heavier bosons, such as axions with mass around 10⁻5 10^-5 10⁻5 eV, could form much smaller, denser objects. This scaling emerges naturally from dimensional analysis of the field equations and sets a fundamental scale for these objects based on the Compton wavelength of the bosons. The mass-radius profile differs radically from that of neutron stars or white dwarfs and may even exhibit regions of gravitational instability depending on the self-interaction term in the potential energy of the field. In scenarios where boson stars form through gravitational cooling or parametric resonance in the early universe, they could act as the building blocks of dark matter halos or populate the cosmic web as relics of inflationary dynamics. Their formation might also be catalyzed by the collapse of scalar field fluctuations trapped in local minima of the potential during symmetry-breaking transitions in the early cosmos. Depending on the specific self-interacting potential, e.g., quartic lambda divides 4 lambda divides 4 or axion-like periodic forms, the compactness and lifetime of the boson star will vary, with stability regions mapped out via numerical relativity. Importantly, boson stars can evade observational bounds that constrain other dark matter models, such as warm dark matter or machos. Since they do not emit radiation and interact only gravitationally, they remain viable even in regimes ruled out for baryonic candidates. They are also not constrained by nucleosynthesis or cosmic microwave background distortions, making them ideal reservoirs of invisible mass that contribute to gravitational lensing and galaxy formation without altering the success of the standard cosmological model. Because boson stars are fundamentally quantum gravitational in nature, their internal structure lacks the traditional layering seen in fermionic stars. Instead of having a distinct core or surface, the scalar field smoothly decays from a central peak outward, resulting in a solitonic density profile governed by the solution of the coupled Einstein-Klein-Gordon system. This continuous structure prevents the formation of shocks or discontinuities, offering remarkable dynamical stability under a variety of perturbations, especially in the case of non-relativistic, ground-state configurations. Some models introduce self-interactions between the bosons to enhance stability or increase mass capacity. A repulsive quartic term in the scalar potential, for instance, allows the star to support more mass before collapsing into a black hole. These self-interacting boson stars can mimic black hole masses up to millions of solar masses, and still lack an event horizon, potentially explaining the massive dark objects found in galactic centers without invoking true singularities. Unlike black holes, however, boson stars exhibit no information paradox and no horizon-based entropy, making them fascinating candidates for resolving quantum gravity puzzles. Boson stars are also a natural setting for exploring the interaction between quantum coherence and curved spacetime. The entire configuration can be interpreted as a macroscopic quantum state maintained in dynamic equilibrium by gravity, similar to a Bose-Einstein condensate held together by a trap potential. In curved spacetime, the scalar field exhibits time-dependent oscillations at a characteristic frequency related to the total mass and field mass, leading to a complex interplay of harmonic structure and relativistic redshift. Excited states are also possible, though typically unstable, and decay into the ground state by emitting scalar radiation or fragmenting into multiple lower-energy boson stars. From an observational standpoint, boson stars offer an exciting frontier for astrophysical searches. Precision pulsar timing arrays may detect subtle anomalies in timing residuals caused by gravitational interactions with nearby compact bosonic structures. Space-based interferometers like LISA may register the unique gravitational wave signatures of boson star mergers, featuring longer in-spiral phases and distinct post-merger echoes due to the absence of a horizon. Additionally, lensing surveys might identify microlensing events with durations and intensity patterns inconsistent with baryonic objects but matching the predicted boson star models. In the regime of ultralight dark matter, boson stars may form the dense solitonic cores observed in simulations of fuzzy dark matter. These soliton cores exhibit core density profiles that address small-scale problems in cold dark matter cosmology, such as the cusp core problem and missing satellite problem. Numerical simulations show that galaxies with such solitonic cores embedded in extended halos of scalar field interference reproduce observed rotation curves and satellite distributions more accurately than traditional CDM models. In certain supersymmetric extensions of the standard model, bosonic fields emerge naturally as partners to fermions, and their stability can be protected by conserved global or gauge symmetries. This leads to scenarios where non-topological solitons like cueballs may form, closely related to boson stars but stabilized not only by gravity, but by conserved nodal charge. If such configurations survive cosmological evolution, they could coexist with or even outnumber conventional boson stars. The richness of these models extends further in supergravity and string-theoretic frameworks, where compactification moduli, axion-like particles, and dilatant fields all contribute scalar degrees of freedom with cosmologically relevant properties. These fields may couple non-trivially to the metric or to each other, leading to multi-field solitonic objects with complex internal structures, oscillatory phases, and long-range interference patterns. Rotating boson stars present yet another layer of complexity. Unlike fermionic stars, which rotate as rigid bodies, boson stars exhibit quantized angular momentum, with rotational quantum number MMM directly tied to the phase winding of the scalar field. The result is a structure that may lack a central density peak and instead form toroid or vortex ring topologies. These configurations are stabilized through centrifugal repulsion balanced by gravitational attraction and scalar field self-coherence. In numerical simulations, such stars display intricate stability landscapes, with some rotational states being metastable and others prone to decay into lower energy configurations or gravitational collapse. Their gravitational wave signals would differ subtly but detectably from those of non-rotating mergers, especially if frame-dragging effects generate additional precession. The possibility of electromagnetic observables remains a matter of ongoing debate. If bosons couple weakly to photons, as in axion photon interaction models, then under strong magnetic fields, such as those near neutron stars, conversion between photons and scalar quanta can occur. This might manifest as polarization anomalies in X-ray or radio emissions, or in spatially dependent spectral modulations. Observations of rapidly rotating neutron stars, magnetars, have already hinted at unexplained features in polarization patterns, leading to speculative connections with axion clouds or even ambient scalar halos. Whether these effects can be attributed to diffuse boson fields or coherent bound structures remains an open and pressing question. In the nonlinear regime, boson stars may engage in chaotic interactions. Collisions between two stars can result in outcomes that depend sensitively on initial velocities, phase alignment, and relative mass. Depending on parameters, the final object might be a more massive stable boson star, a dispersal into scalar radiation, or prompt collapse into a black hole. Some simulations reveal bouncing events, where stars temporarily merge and separate multiple times before settling. These dynamics are inaccessible to purely Newtonian models and require full general relativistic treatment. The emitted gravitational radiation from such encounters could provide smoking gun signatures for identifying bosonic compact object interactions. The role of boson stars as alternatives to black holes continues to generate interest. Because they lack an event horizon, infalling matter may generate electromagnetic or neutrino signatures absent in true black holes. Furthermore, their central region is non-singular, potentially allowing information preservation and avoiding paradoxes associated with singularity theorems and Hawking radiation. This places boson stars in a unique position as test cases for quantum gravity proposals, including those invoking holographic principles, modified entropy bounds, or effective geometries derived from loop quantum gravity or causal dynamical triangulations. In the limit of vanishing self-interaction, boson stars behave as pure gravitational condensates. In this regime, the scalar field mass sets a unique scale for the system. If the field is ultralight, on the order of 10⁻22 10⁻22 10⁻22 eV, the de Broglie wavelength becomes kiloparsec scale, leading to suppression of small-scale structure formation and providing a natural explanation for the observed absence of substructure in dwarf galaxies. The resulting cosmological models predict smooth, cored dark matter halos with central solitonic profiles and outer interference zones governed by Schrödinger-Poisson dynamics. These features are being compared directly to data from low-surface brightness galaxies and dwarf spheroidal rotation curves. Field-theoretic descriptions of boson stars in curved spacetime raise important questions about the nature of locality, vacuum stability, and particle identity. The scalar field forming the star is not made of individual particles in any traditional sense but of a continuous, coherent excitation of the field itself. Particle creation and annihilation are replaced by collective behavior, much like phonons in a crystal lattice or excitons in condensed matter systems. This suggests a blurring of the distinction between classical and quantum, especially in gravitational contexts, where spacetime curvature and field oscillations are tightly interlinked. Observables associated with such structures may challenge conventional particle-based detectors, requiring novel techniques for identifying coherence, phase transitions, or decoherence events on astrophysical scales. The presence of boson stars in the cosmic inventory would imply that the fabric of the universe contains stable, long-lived configurations of scalar fields, coexisting with, and in some cases replacing, conventional matter structures. This raises profound questions about the initial conditions of the universe and the role of quantum fields in the formation of complexity at macroscopic scales. Scalar fields that remain light and coherent through the epoch of recombination and beyond must have been protected from quantum corrections and radiative instability, suggesting that boson stars are not accidental byproducts but perhaps inevitable consequences of the symmetries encoded in fundamental physics. In inflationary cosmology, scalar fields are already central players, driving exponential expansion and seeding density perturbations via quantum fluctuations. These same scalar fields, or their remnants, could later fragment and condense into localized lumps, especially if the inflationary potential includes flat directions or shallow minima. In such scenarios, the post-inflationary universe may have been populated by a network of scalar condensates, some of which collapsed under self-gravity into boson stars. These objects could serve as relics of high-energy physics, encoding in their mass, radius, and field profile a memory of symmetry-breaking scales and reheating temperatures. Phase transitions in the early universe may also give rise to topological or non-topological defects, such as domain walls, cosmic strings, or cueballs, that evolve into or coexist with boson stars. The dynamics of these transitions are governed by non-equilibrium field theory, where the interaction between scalar gradients and metric fluctuations determines whether such structures survive or dissipate. In cases where the field is complex and possesses a conserved global charge, the resulting boson star can be stabilized against decay even in the absence of significant self-interaction, maintained purely by the gravitational potential and the coherent oscillation of the scalar wave function. Within string theory compactifications, the landscape of possible vacuum configurations includes numerous axion-like particles, moduli, and dilatant fields, each associated with its own potential and symmetry structure. These fields can be dynamically light and cosmologically active, forming bound states that function as boson stars in 4 dimensions. In certain duality frames, these boson stars are mapped to wrapped brane configurations or coherent D-instanton effects, implying that the existence of boson stars could provide an observational bridge between low-energy astrophysics and high-energy string dynamics. If boson stars form through such mechanisms, their detection would offer direct evidence of extradimensional physics and the compact topology of the bulk space. In models of modified gravity, such as scalar tensor theories or F-R extensions, the scalar fields responsible for boson stars may also mediate deviations from general relativity at intermediate or strong field scales. These deviations might be manifest in orbital precession, gravitational redshift, lensing profiles, or the timing of binary pulsars. Detailed modeling of scalar field behavior in these theories reveals that boson stars can exist with enhanced compactness or modified mass-radius relationships, placing them at the boundary between ordinary stars, black holes, and exotic compact objects. As detectors become more precise, these deviations can be probed to test not only the existence of boson stars, but also the validity of general relativity in previously inaccessible regimes. The information content of boson stars remains an area of speculation. Because they are non-singular, bounded, and horizonless, they may provide a resolution to the black hole information paradox. In principle, infalling matter into a boson star is not lost to a singularity or cloaked behind a horizon, but is gradually absorbed into the scalar field condensate, altering its global phase, oscillation frequency, or internal configuration. Whether such changes are measurable or recoverable is a matter of debate, but it opens the possibility that boson stars act as information-preserving storage structures, akin to gravitational memory devices. This would dramatically revise our understanding of entropy, decoherence, and the thermodynamics of spacetime. Boson stars challenge the idea that astrophysical compactness must be accompanied by opacity. Their transparency to radiation, coupled with their gravitational depth, allows for environments where high-energy interactions can take place without the conventional shielding of an event horizon. In such regions, photons, neutrinos, and even gravitational waves could be scattered or lensed in distinctive ways, potentially giving rise to observable phenomena not explainable by standard compact object models. If boson stars accrete baryonic matter, they might develop photospheres or thin atmospheres, temporarily behaving like faint stars or accreting objects without the high-energy jets associated with black holes or neutron stars. At the mathematical level, the study of boson stars continues to push the boundaries of numerical relativity and nonlinear field dynamics. Solving the full Einstein-Klein-Gordon system in 3+1 dimensions, especially for rotating or multi-field configurations, requires adaptive mesh refinement, gauge fixing, and careful stability analysis. These simulations are not merely academic, they provide direct templates for gravitational wave detectors, offer insight into the fate of scalar instabilities, and illuminate the spectrum of gravitational solitons that may populate the dark sector of the universe. The comparison between boson stars and neutron stars provides a revealing contrast between fundamentally different forms of compact matter. Neutron stars are governed by nuclear degeneracy pressure, with their internal structure determined by the equation of state of baryonic matter at supranuclear densities. Their composition includes layers of neutron-rich plasma, crusts of exotic nuclei, and possibly cores of hyperons or deconfined quark matter. Boson stars, by contrast, are governed not by particle collisions or thermodynamic pressure, but by the coherence of a scalar field oscillating in a gravitational well. There are no shells, no crust, no core, only a smooth field configuration whose energy density is distributed continuously, often peaking at the center and decaying exponentially with radius. Mass-radius relationships further highlight their differences. While neutron stars exhibit an upper mass limit, the Tolman-Oppenheimer-Volkoff limit, of around 2.5 solar masses, depending on the equation of state, boson stars can theoretically exist across a far wider mass range, from asteroid mass microstars composed of heavy bosons, to galactic mass giants made of ultralight fields. Their radii can likewise vary by many orders of magnitude, depending on boson mass and interaction strength. The result is a population of objects that may be observationally degenerate with neutron stars, black holes, or even diffuse halo cores, but whose internal physics is entirely different. Boson stars may also play a role in cosmic archaeology, the study of primordial structures left over from the earliest phases of the universe. If scalar fields formed solitonic configurations shortly after inflation, these objects could have survived to the present day as fossils of the early universe, preserving information about high-energy physics and symmetry-breaking processes that no longer leave observable traces in the cosmic microwave background or baryonic matter distribution. These stars could be embedded in galaxy halos, orbiting the Milky Way as dark, isolated compact halo objects, dicas, or clustered in filamentary networks that trace the scalar field interference patterns of the young universe. High-resolution cosmological simulations using Schrödinger-Poisson methods have begun to explore the formation and evolution of such soliton cores, showing how interference and wave turbulence shape large-scale structure in models of fuzzy dark matter. In these simulations, dark matter halos develop dense, stable centers surrounded by chaotic, interference-driven outer regions, behaviors inconsistent with classical particle dark matter but natural for coherent wave-like fields. These solitonic centers match analytical solutions for boson stars in the non-relativistic limit, reinforcing the idea that boson stars may serve as both dark matter constituents and structural seeds of galaxies. Simulations also show that mergers of halos containing solitonic cores can lead to gravitational cooling, phase mixing, and the emergence of a new central boson star. These results imply that boson stars are not merely static relics but dynamic entities that can evolve, merge, and reform, participating in the cosmic web like any other astrophysical object, but governed by quantum field coherence rather than thermal physics. Unlike collisionless dark matter particles, boson stars can interfere, diffract, and form standing waves on kiloparsec scales, leading to novel astrophysical phenomena such as oscillating halo densities, breathing modes, or phase instability cycles. In scenarios where boson stars coexist with other compact objects, such as neutron stars or black holes, their gravitational interactions can lead to hybrid systems with unique dynamics. For example, a boson star orbiting a black hole may undergo tidal disruption, spilling scalar field into the black hole's vicinity and generating scalar gravitational interaction signatures. Conversely, a boson star may accrete onto a neutron star, modifying its moment of inertia or shifting its timing properties, potentially observable through pulsar timing arrays. In binary mergers involving one or two boson stars, the absence of a hard surface or horizon alters both the in-spiral waveform and the post-merger remnant, making these events promising targets for multi-messenger astronomy. There is also increasing interest in boson stars as theoretical laboratories for testing quantum gravity, especially in semi-classical regimes where curvature is strong but Planck scale effects remain subdominant. Because they lack singularities and possess finite total energy, boson stars offer an ideal setting for probing the behavior of quantum fields in curved spacetimes, including questions about renormalization, entanglement entropy, and backreaction. The absence of a horizon eliminates the ambiguity associated with transhorizon correlations, allowing for well-defined global quantum states. This makes boson stars potential testbeds for exploring the validity of semi-classical approximations, or for modeling holographic duals in ADS/CFT correspondence. In a more speculative direction, some models propose that boson stars might exhibit quantum interference effects on macroscopic scales. If two such stars overlap, their scalar fields may interfere constructively or destructively depending on phase alignment, leading to oscillatory density patterns, soliton fusion, or even cancellation. These behaviors, though difficult to observe, represent a radical departure from classical expectations and suggest that the universe may contain truly quantum structures on kiloparsec scales, entities that behave not as classical particles or fields, but as coherent quantum condensates whose fate depends on interference and entanglement. The quantum information aspects of boson stars open a gateway to one of the most intriguing frontiers of modern physics, the nature of coherence, entanglement, and decoherence in gravitationally bound macroscopic quantum systems. Unlike ordinary matter configurations, where thermalization and statistical mechanics dominate, boson stars remain in a coherent, pure-state regime, potentially preserving quantum phase information across cosmological timescales. The scalar field that forms a boson star does not dephase or scatter in the usual thermodynamic sense, rather, it maintains a unified oscillatory identity, described by a global phase and frequency. This implies that boson stars could serve as natural quantum memory structures, storing information about initial conditions in a gravitationally protected state. Decoherence in such systems is an active area of theoretical research. In standard quantum mechanics, interactions with an environment cause a pure quantum state to evolve into a mixed state, destroying interference and entanglement. For boson stars, however, the environment is the curvature of spacetime itself. Studies suggest that the gravitational field may act as a weak decoherence channel, nonlinear but non-dissipative, allowing partial retention of quantum information over enormous durations. Some models even propose that boson stars might be quantum error-correcting geometries, wherein the structure of the spacetime prevents phase errors from accumulating chaotically, a gravitational analog to topological protection. If this is true, boson stars could be not only astrophysical entities but quantum coherent objects writ large, functioning as long-lived repositories of information about the early universe. Their field configurations might encode the symmetry-breaking patterns from grand unification epochs, relic phase alignments from inflation, or subtle correlations seeded by vacuum fluctuations. If two boson stars formed from the same fluctuation domain, they may retain phase correlations even when separated by cosmological distances, raising the question of whether macroscopic quantum entanglement could persist through cosmic expansion. This possibility connects boson stars with modern ideas in quantum gravity and holography. In particular, AD/CFT duality suggests that certain strongly coupled quantum field theories can be equivalently described by gravitational dynamics in higher dimensions. In such contexts, boson star solutions have been found in asymptotically AD spacetimes, where they correspond to thermalized or coherent phases in the dual field theory. These gravitational solitons thus become holographic images of quantum states, bridging the geometry of spacetime with the structure of information in a non-gravitational language. The stability, collapse, and oscillatory behavior of boson stars in ADS may mirror phase transitions, decoherence events, or information scrambling in the boundary CFT, providing deep insight into how spacetime geometry emerges from quantum entanglement. Analogous ideas arise in proposals like the ER=EPR conjecture, which posits that entangled particles may be connected through non-traversable wormholes. In this view, the coherence of a boson star could be interpreted as a network of microscopic entanglements, stitched together across its internal structure. If two boson stars were entangled at formation, their joint evolution might trace a kind of non-local, quantum-connected geometry, suggesting the radical idea that the large-scale structure of the universe contains entanglement topology, not just classical curvature. Beyond theory, these ideas motivate experimental analogues. Laboratory systems using Bose-Einstein condensates, photonic lattices, or ultra-cold atoms in optical traps allow for the simulation of curved space field dynamics, interference between condensates, and even synthetic gravitational potentials. These platforms have demonstrated phenomena strikingly reminiscent of boson star behavior, soliton formation, quantum vortex dynamics, interference patterns, and long-lived oscillatory modes. Experiments have engineered nonlinear self-trapping, where a localized wave packet resists dispersion, precisely the mechanism that stabilizes boson stars in relativity. By introducing controlled decoherence channels, researchers can test how such systems lose coherence, offering direct insights into what might happen to their astrophysical analogues over billions of years. In cosmology, the presence of such coherent scalar condensates challenges our understanding of entropy and arrow of time. Standard thermodynamics predicts increasing disorder, yet boson stars persist as islands of coherence, resisting entropic decay. This invites the idea that the early universe may have seeded coherence, a kind of anti-entropic initial condition that allowed for the emergence of stars, galaxies, and complexity. Boson stars, in this framing, are not just exotic objects, but archaeological records of order, frozen waves from a time before entropy reigned. Some speculative proposals go even further, imagining civilizations capable of engineering boson stars as information storage devices, long-term energy reservoirs, or even quantum computational substrates. Such structures would be essentially undetectable through electromagnetic means, gravitationally subtle, and protected from noise by their isolation and coherence, ideal components for a Type 2 or 3 Kardashev-level intelligence. These ideas remain far from testable, but they illustrate the fertile crossroad where boson stars lie, between quantum information, general relativity, and cosmic evolution. If boson stars are real, their very existence challenges deeply held assumptions about what it means to observe or detect an object in the universe. They do not emit light, do not reflect it, and may not even significantly interact with ordinary matter, yet they can shape entire galaxies, bend spacetime, and perhaps encode information in ways not yet understood. This makes them prime candidates for unseen realities, entities that exist, persist, and influence the cosmos while remaining almost entirely invisible to human senses and most instrumentation. From a philosophical standpoint, boson stars exemplify the tension between ontological presence and epistemic accessibility. They are real in the gravitational sense, they curve spacetime, influence orbits, and can participate in cosmic dynamics. But in every other way, they may remain fundamentally silent, dark in all bands, featureless in structure, and reducible only to mathematical objects in simulations or abstract signatures in gravitational waveforms. In this way, they resonate with the concept of noumena, Kantian things in themselves, existing independently of observation and only partially revealed through indirect effects. Yet boson stars also pose a mirror to the observer. If such stars can exist undetected for billions of years, and if entire galaxies could host them at their cores or carry them as companions, then the limits of observation become not just technical, but conceptual. Perhaps we have already seen their effects, in lensing anomalies, in unexplained timing variations, in halo density profiles, but misattributed them to conventional phenomena. The challenge is not just to improve our telescopes, but to widen our interpretive frameworks, to admit that the universe may contain coherent, massive, field-based entities unlike anything in our standard taxonomies of stars, planets, and particles. In the context of dark matter, boson stars offer a rare possibility, not just a medium, but a structure. Whereas most models of dark matter treat it as a statistical fluid, a diffuse sea of non-interacting particles, boson stars represent islands of form within the formless, standing waves where darkness becomes ordered. If dark matter is made of ultralight scalar fields, then some fraction of it may clump into stable configurations, and these structures may provide the architecture upon which luminous matter assembles. Galaxies would thus not merely be embedded in dark matter, they would be sculpted by its internal coherence, tracing the interference patterns of fields invisible to light. On cosmological scales, this introduces a layer of hidden geometry to the universe. Not only is spacetime curved by mass, but mass itself may be shaped by the phase structure of quantum fields extending across megaparsecs. In this view, boson stars are like nodes in a cosmic standing wave, a harmonic infrastructure underlying the filamentary web we observe. What we see as voids and clusters may be surface effects, the visible skin over a deeper, more subtle vibration in the quantum gravitational field. Detecting boson stars would not just confirm a particle theory, it would uncover an entire field-based architecture of the cosmos. Such structures also provoke questions of cosmic identity and continuity. If a boson star persists for billions of years, unchanging in composition, coherent in phase, does it remember its formation? Could such an object, lacking entropy, immune to thermodynamic decay, serve as a kind of cosmic memory? What might it mean for the universe to contain regions where time barely flows, where the arrow of entropy is suppressed, where matter is frozen not by temperature, but by quantum phase locking? In this view, boson stars are not just remnants, but witnesses, silent observers of the universe's evolution, untouched by fusion, by chaos, by decay. This lends itself to metaphysical reflections. Boson stars exist at the edge between being and non-being, too subtle to glow, too massive to ignore. They are almost not there, but the gravitational field does not lie. Their presence forces us to rethink what constitutes objecthood in physics. They are not made of particles in the traditional sense. They do not have surfaces, nor boundaries. Their matter is smeared, delocalized, governed not by location but by amplitude and frequency. If particles are points, and stars are sums of particles, then boson stars are whispers of existence, organized not by collisions, but by resonance. Perhaps the deepest implication of boson stars is epistemological. They require us to believe in things we cannot directly see, but whose reality is no less certain for being silent. In a universe where light cannot reach every structure, and where coherence can substitute for contact, boson stars are not an exception, they are a hint. A hint that the cosmos is wider, stranger, and more continuous than our detectors yet imagine. They are, perhaps, the poetry of dark matter, an unseen rhythm, a pulse of the invisible, a stable vibration at the edge of thought. ChatGPT. If boson stars are woven into the deep structure of the cosmos, then they may play a foundational role in galaxy formation and cosmic evolution. In the earliest epochs of the universe, when matter was still a nearly uniform plasma and fluctuations had barely begun to grow, the seeds of future galaxies emerged from tiny perturbations imprinted during inflation. While cold dark matter provides the gravitational scaffolding in standard models, boson stars offer a more structured and coherent alternative, preformed gravitational solitons that could have served as nuclei for galactic collapse. Because boson stars can form from scalar field fragmentation shortly after inflation, they may have preceded even the formation of baryons. Their presence in the early universe would offer deep gravitational wells, quiet, non-interacting, and persistent, around which baryonic matter could cool, collect, and condense. In this scenario, the first galaxies did not form from stochastic aggregation alone, but rather grew around pre-existing nodes of coherence, silently guiding the architecture of the cosmos. These coherent masses could enhance structure formation without introducing the small-scale clustering problems that plague traditional cold dark matter models. Their internal stability and lack of feedback, no radiation pressure, no supernovae, no heating, would allow them to persist undisturbed, embedded within the halos of galaxies as invisible architects. They would not disrupt star formation, but they would shape gravitational potential wells in subtle, persistent ways. Their presence might be inferred not from excess radiation or violent events, but from the shape of rotation curves, the distribution of stellar velocities, or the smoothness of halo density profiles. Where cold dark matter clumps chaotically, boson stars stabilize, introducing quantum smoothness to an otherwise jagged gravitational landscape. Over billions of years, these invisible masses could drift, merge, or even fall into galactic centers. Some may become supermassive, either by slow accretion of scalar field or by coalescing with others. If such objects reside in the hearts of galaxies, they offer an alternative to black holes, massive, compact, and gravitationally dominant, but without event horizons, without singularities, and without Hawking radiation. In this model, the active galactic nuclei we observe may not be black holes at all, but boson star cores, their emissions coming not from accretion disks disappearing into nothingness, but from matter spiraling around a core of coherent, silent field. This leads to testable differences. The lensing of light around a boson star lacks the sharp edge of a black hole shadow. The timing of light echoes, the patterns of quasi-periodic oscillations, the spectrum of gravitational wave ring-downs, all differ subtly. And it is in these differences that the true nature of the core might be revealed. As instruments like the Event Horizon Telescope, LISA, and SKA improve, the possibility of distinguishing a boson star from a black hole will become a central test of both gravity and matter in the strong field regime. At even larger scales, boson stars could be the quantum nodes of the cosmic web. The filamentary structure of the universe, seen in galaxy surveys and simulations, may be more than just the result of gravitational collapse. It may be a reflection of interference patterns of ultralight scalar fields, with boson stars sitting at the antinodes, massive points where coherence is maximized and field energy condensed. This would mean that the universe is not merely structured by matter clustering under gravity, but patterned by phase coherence, by oscillations frozen since the earliest times. These patterns could extend into voids as well. Where the density of galaxies is low, boson stars may drift alone, invisible, silent, and stable. Their gravitational presence could affect cosmic microwave background anisotropies, gravitational lensing of distant quasars, or the flow of galaxies across supercluster boundaries. In essence, they may act as quantum tracers of the invisible, telling us not just where matter is, but where it remembers being, because the scalar fields from which they formed carry not just mass, but memory of phase and formation. This brings us back to the philosophical: boson stars are not just objects. They are histories. They are scars in the field, echoes of primordial symmetry, crystallizations of the quantum vacuum. They do not burn. They do not shine. But they remember. Their frequency is their fingerprint. Their mass is their story. They are cosmic poems written in scalar amplitude, resonating still across the void. And so, in the structure of galaxies, in the shape of the cosmic web, in the silence of voids, boson stars may be watching, anchoring the universe not in collision, but in coherence. ChatGPT. Perhaps, in the end, Boson stars remind us that not all that is real must blaze with light. Some truths are quiet. Some structures endure not through fire or noise, but through stillness, coherence, and hidden rhythm. These stars, composed not of atoms but of undying waves, speak in gravity and silence. They are not the triumph of fusion, but the persistence of form. Not born in cataclysm, but crystallized from the deep breath of the vacuum itself. To find them is to look past brightness, past the loudness of explosions and the drama of collapse, into a subtler layer of the universe, where existence is phase-locked, time is slow, and memory is written not in light but in mass and geometry. Whether as relics of the early cosmos, seeds of galaxies, or messengers from a deeper layer of physical law, boson stars are not anomalies. They are signals. Silent, coherent, gravitational whispers of a universe more unified than we ever dared to imagine. And so, somewhere out there, beyond the reach of light, they wait, not to be discovered, but to be understood.
In the vast, silent reaches of the interstellar medium, where temperature drops to just a few degrees above absolute zero, a whisper of matter begins to stir. Invisible to the human eye, a faint density fluctuation, no more than a seed of dust and gas, drifts within a giant molecular cloud. It is neither bright nor hot. It does not yet shine. And yet, this trembling condensation holds the promise of a star. Gravity, patient and relentless, begins its quiet work. It draws the gas inward, wrapping the fragment tighter with every passing millennium. The cloud core shrinks, compressing under its own weight, growing warmer and denser. What was once a tranquil region of dust now churns with turbulence, magnetized filaments coiling around the collapsing core like skeletal scaffolding of future brilliance. As the gas falls inward, it forms a flattened disk, spinning ever faster due to conservation of angular momentum. At the center of this growing structure lies the protostar, a hidden ember deep within an opaque cocoon. It is not yet a true star, for fusion has not begun, but already it radiates in the infrared, its warmth a silent prelude to what is to come. The dust surrounding it glows faintly, echoing the heat of compression and the friction of infalling matter. Jets of plasma erupt from the poles, slicing through the surrounding cloud like lances of energy. These bipolar outflows help clear away excess material, regulating the mass accretion and shaping the stellar environment. Magnetic fields thread through the forming disk and jets, guiding the newborn star's earliest breaths. The protostar grows heavier, hotter, more luminous. Hidden from view, nuclear pressure builds in its core. There comes a moment, a threshold, when the temperature at the center rises above 10 million Kelvin. Hydrogen nuclei, once content to drift alone, begin to fuse. With that ignition, the protostar crosses a boundary into stellar life. It becomes a main sequence star, no longer fed solely by collapse, but by the energy of its own reactions. The cocoon begins to thin. Light, once imprisoned, escapes. From darkness, from cold, from disorder, emerges the fire of a star. The dust that once veiled the light becomes the very ingredient of planetary systems, of moons, of oceans, and of life. Every heartbeat, every atom of calcium in a bone or iron in blood, was forged in a process that began with that quiet collapse. Before the brilliance, there was silence. Before fusion, there was falling. Before light, there was only shadow. Observations of protostellar evolution have been revolutionized by infrared and submillimeter astronomy. Telescopes like the James Webb Space Telescope and ALMA peer into the thick veils of dust that obscure these early phases, revealing disks, jets, and magnetic turbulence that shape the path to stardom. These instruments capture light that has traveled for thousands of years, emitted not by nuclear fusion, but by the friction of collapse and the glow of accretion shocks. Protostars are classified by their spectral energy distributions into stages, class 0, 1, 2, and 3, each marking a distinct chapter in the transformation from dense core to luminous star. In the earliest stage, Class 0, the object is entirely enshrouded in its envelope, with more mass in the surrounding cloud than in the protostar itself. As it accretes matter and grows, it moves into Class 1, where the central source dominates, and the envelope begins to dissipate. Class 2 marks the emergence of a visible star with a prominent disk, the birthplace of future planets. Finally, Class 3 denotes a star that has largely shed its disk, now entering maturity. Magnetohydrodynamic simulations of protostellar collapse provide deep insights into the complex interplay of gravity, rotation, pressure, and magnetic fields. These models show that without angular momentum loss, mediated by magnetic braking or jet-driven outflows, a protostar could not efficiently accrete material. Magnetic reconnection events within the disk may also trigger bursts of accretion, a phenomenon observed in so-called Fu-Orioni stars, whose brightness can increase by a factor of 100 over a few months. Chemical evolution during these early stages is equally profound. As dust grains migrate inward, they undergo heating, triggering the release of ices and complex organic molecules. These molecules, formaldehyde, methanol, acetylene, and even prebiotic precursors, can seed the future planetary system. Thus, even before the star begins fusion, the conditions for chemistry and ultimately biology are quietly taking shape. In binary systems, the story grows even more intricate. Interactions between protostars, their disks, and shared envelopes can lead to mass transfer, spiraling dynamics, and the eventual formation of tightly bound pairs or even stellar mergers. These processes not only affect the stars themselves, but can trigger the formation of massive planets or brown dwarfs through gravitational fragmentation of the disk. The birth rate of stars, or star formation rate, is a key parameter in galactic evolution. Protostellar populations in nebulae like Orion or Perseus serve as cosmic laboratories, where thousands of forming stars at various stages can be observed simultaneously. These studies inform models of galaxy growth, stellar feedback, and even the cosmic cycle of matter, from diffuse gas to stellar cores to supernovae and back again. The physics of protostellar accretion disks remains a frontier of astrophysical research. These rotating structures, composed of gas and dust, transport angular momentum outward while funneling mass inward toward the growing star. The primary mechanisms driving this transport, magnetorotational instability, MRI, gravitational instabilities, and disk winds, are actively studied using high-resolution numerical simulations and multi-wavelength observations. MRI, in particular, relies on the presence of weak magnetic fields to induce turbulence, allowing angular momentum to be redistributed efficiently within the disk. Observations with ALMA have revealed detailed substructures in many young disks, such as concentric rings, gaps, and spiral arms. These features may indicate early planet formation or interactions with stellar companions. The discovery of dust traps, regions where particles concentrate due to pressure gradients, supports models in which millimeter-sized grains aggregate into planetesimals even before the star reaches the main sequence. Thus, the architecture of planetary systems may be established while the star itself is still in its embryonic phase. Isotopic studies of meteoritic material in our own solar system suggest that the Sun's protostellar disk was chemically and thermally heterogeneous. Short-lived radionuclides like aluminum-26, likely injected by a nearby supernova or massive star wind, provide evidence that the early solar system formed in a rich stellar nursery, not in isolation. This environment may have influenced the distribution of volatiles and organics that later shaped Earth's atmosphere and biosphere. Gravitational interactions between protostars and their surrounding cloud cores also play a decisive role. Recent simulations show that turbulence in molecular clouds can induce fragmentation, leading to clustered star formation. These fragments may compete for gas, influencing the mass distribution of newborn stars, known as the initial mass function, IMF. Understanding the IMF is crucial for modeling galactic luminosity, stellar evolution, and the chemical enrichment of the interstellar medium. Meanwhile, the feedback from young protostars is far from passive. Bipolar jets and wide-angle winds inject momentum and energy into the cloud, carving out cavities and potentially triggering or suppressing further collapse in neighboring regions. Observations with instruments like SOFIA and Herschel have revealed complex shock structures and ionized flows extending light-years from their source. These outflows regulate both the growth of the protostar and the structure of its stellar nursery. On cosmic timescales, protostellar formation contributes to the grand feedback loop of the universe. Stars born in dense clouds enrich their surroundings through stellar winds, radiation, and eventual supernova explosions, seeding the next generation of stars with heavier elements. The cycle of collapse and ignition, of darkness becoming light, is not just a physical process but a cosmic rhythm, threading together the past and future of galaxies. At the scale of galaxies, protostellar formation is tightly linked to the dynamics of spiral arms, bars, and gas inflows. In spiral galaxies like the Milky Way, density waves compress interstellar gas along the arms, creating the ideal conditions for molecular cloud collapse. These spiral shocks slow down the gas relative to the stars, allowing regions of higher density to build up. Inside these pockets, gravity eventually overcomes pressure and turbulence, giving birth to protostars en masse in what are known as stellar nurseries. Galactic bars, too, can funnel gas toward the central regions of galaxies, boosting the star formation rate and sometimes triggering nuclear starbursts. These intense periods of star birth can form thousands of protostars per year in a compact region, as seen in starburst galaxies like M82. There, the interstellar medium becomes a chaotic environment filled with shock waves, strong magnetic fields, and overlapping feedback from jets and winds, producing extreme conditions that test the limits of current theoretical models. In the early universe, the very first protostars, known as population 3 stars, formed under radically different conditions. Lacking metals, elements heavier than helium, these primordial gas clouds could not cool efficiently, leading to the formation of stars that were likely far more massive than those born today, some exceeding hundreds of solar masses. These colossal stars burned quickly and died violently, enriching their surroundings with the first heavy elements and setting the stage for the next generations of protostars. Modern cosmology aims to model these first luminous objects, using simulations that combine hydrodynamics, chemistry, radiation transfer, and gravity in 3 dimensions. These simulations suggest that protostellar disks existed even in the first billion years of cosmic time, and that fragmentation in these early disks may have produced binary or multiple systems, similar to what we see in today's star-forming regions. Observations by JWST are beginning to reveal galaxies at redshifts beyond 10, where early protostellar populations may still be faintly detectable. Even now, many of the deepest questions remain. What sets the mass of a star at birth? Why do some regions of galaxies form stars prolifically, while others remain quiescent? What mechanisms determine whether a collapsing gas core becomes a brown dwarf, a star, or an object on the edge of both? Answering these questions requires not just observation, but theoretical insight, connecting physical laws from plasma physics and thermodynamics to the large-scale structure of the cosmos. In the end, the study of protostars is more than an investigation into beginnings. It is a search for continuity between the simplest atomic clouds and the complex architectures of planetary systems. From a single dust grain to a nuclear furnace, from gravitational collapse to the ignition of light, every step in the life of a protostar echoes in the broader story of cosmic evolution. High-mass protostars, those destined to become stars more than 8 times the mass of the Sun, present a distinct challenge to both observation and theory. Unlike their low-mass counterparts, they evolve rapidly, reaching the main sequence while still accreting material. Their powerful radiation fields, intense stellar winds, and strong UV output begin to ionize and disrupt their surroundings even before accretion ends. This interplay between continued growth and self-destruction makes massive star formation a finely balanced and turbulent process. Observationally, massive protostars are rare and tend to form in distant, obscured regions of the galaxy, buried deep within dense cores of giant molecular clouds. Instruments like ALMA and the Very Large Array allow astronomers to probe these regions at radio and submillimeter wavelengths, revealing clustered star formation, complex filamentary structures, and rapidly rotating disks around massive cores. In many cases, these disks are unstable, fragmenting under their own gravity and possibly giving rise to secondary stars or massive planets. Radiation pressure from the forming star poses a fundamental limit to continued accretion. For a time, it was thought that beyond a certain mass, perhaps 20 or 30 solar masses, radiation would prevent any further inflow of gas. However, models now suggest that accretion can continue through dense equatorial disks, where material is shielded from the star's harshest radiation. Moreover, collimated outflows and jets may carve low-density escape channels along the poles, allowing radiation to escape without halting infall entirely. These theoretical insights are increasingly supported by observation. Hypercompact H2 regions, tiny zones of ionized gas enveloping the youngest massive stars, are detected near strong millimeter continuum sources, indicating that accretion and ionization coexist. Maser emission from molecules like water and methanol also trace shocked regions and outflows, revealing complex kinematics around massive protostars. Feedback from high-mass protostars dramatically reshapes their environments. As the protostar grows, it creates a bubble of ionized gas, sweeping up surrounding material into a dense shell. Over time, this shell may become gravitationally unstable, collapsing to form a new generation of stars, a process known as triggered star formation. In this way, massive stars not only disrupt but also catalyze the next wave of stellar birth, propagating a chain reaction of creation across entire molecular complexes. Massive protostars are also key players in galactic evolution. Their short but intense lives end in supernova explosions, injecting energy, momentum, and heavy elements into the interstellar medium. The resulting shock waves can compress nearby gas, mix and distribute metals, and influence the dynamics of the surrounding spiral arms. The seeds of new planetary systems, rich in carbon, oxygen, silicon, and iron, owe their origin to such explosive feedback. Modern research now integrates data from multiple wavelengths and physical regimes, combining radio maps of cold gas, infrared views of warm dust, X-ray emission from stellar shocks, and optical spectroscopy of outflows. Astronomers are building a holistic picture of protostellar evolution. Machine learning and AI-based data analysis are also entering the field, helping classify protostellar objects across vast datasets and identify patterns that elude traditional methods. In every observation of a protostar, whether it is a faint glimmer in the Orion Nebula or a massive core on the brink of collapse in a distant spiral arm, we are witnessing a chapter in the great story of stellar genesis. These are not just stars in the making. They are engines of galactic change, factories of elements, and cradles for future worlds. Their birth is a symphony of gravity, turbulence, radiation, and time, a process still ongoing across the universe, echoing the same ancient rhythm that once brought light to our own sky. Protostellar disks, the swirling structures of gas and dust encircling young stars, are not merely passive bystanders. They are active workshops, planetary laboratories where future worlds take shape. Within these dense, rotating disks, grains of cosmic dust slowly aggregate, forming pebbles, rocks, and eventually planetesimals, the foundational building blocks of planets, moons, asteroids, and comets. Recent observations have dramatically changed our understanding of the timescale and complexity of planet formation. Images from ALMA have captured intricate patterns in these disks, including clear, ring-shaped gaps, spiral arms, and asymmetric dust concentrations. These structures often signal the presence of young planets, orbiting protostars that have not yet fully ignited fusion. Thus, planetary birth may overlap with stellar birth, underscoring how deeply intertwined the two processes truly are. One mechanism underlying these patterns is gravitational interaction. Forming planets carve out gaps by gravitationally clearing orbital paths, redirecting gas flows, and creating local pressure traps. In these traps, dust grains gather and grow more rapidly, potentially catalyzing rapid planetesimal formation. Numerical simulations indicate that these early processes can occur swiftly, perhaps within only a few 100,000 years after protostellar collapse begins, challenging earlier notions of slower sequential growth. Chemistry within protostellar disks also profoundly influences the characteristics of future planetary systems. Variations in temperature and radiation lead to chemical stratification. Volatile substances, such as water and ammonia, condense in colder outer regions, while silicate minerals and metals remain dominant near the warmer inner disk. These compositional gradients eventually translate into different planet types: rocky, terrestrial planets close in, and gas-rich or icy worlds farther out. This framework provides insights into our own solar system's architecture. Studies of meteorites, comets, and primitive asteroids reveal a record of chemical gradients preserved from the protostellar disk era. The distribution of water and organic molecules, essential ingredients for life, was likely established even before Earth formed. Thus, habitability, the potential for life, may trace its roots back to the protostellar environment itself. A particularly intriguing field of research involves analyzing isotopic signatures found in meteorites, which provide clues about the earliest phases of solar system evolution. Short-lived radionuclides and isotopic anomalies, such as oxygen and nitrogen isotope ratios, suggest complex transport processes within the early solar nebula. High-temperature grains forged near the young sun were mixed with icy materials drifting inward from outer regions, creating the heterogeneous environment from which our planets emerged. Advanced modeling now explores the dynamic interplay between magnetic fields, gas dynamics, and dust evolution within disks. Simulations demonstrate how turbulence, driven by magnetohydrodynamic instabilities, influences grain growth, sedimentation, and radial drift. These processes strongly shape where, when, and how planets form. Such models not only reproduce observed disk structures but also predict the conditions necessary for Earth-like planets versus gas giants. Observations of exoplanetary systems further deepen our understanding. The surprising diversity of planet architectures, hot Jupiters, super-Earths, tightly packed planetary systems, challenges simple theories. By tracing these planets' origins back to protostellar disks, astronomers seek universal patterns underlying planet formation, hoping to understand whether the solar system is typical or exceptional. Protostellar disks also serve as natural laboratories for testing theories of physics and chemistry under extreme conditions. Cosmic ray irradiation, ultraviolet exposure, shocks from disk winds and jets, all these influence chemical reactions that generate complex molecules, potentially including precursors to life. Recent detections of amino acid precursors in protostellar environments strengthen the connection between stellar nurseries and biological origins. At its core, the formation of planets is not a separate event, but a natural outcome of the star-forming process. Every planetary system, including our own, began hidden within a protostellar disk, quietly assembling while the central star itself was still awakening. By exploring these cosmic birthplaces, we trace not just our astronomical origins, but also the deeper question of life's place in the universe. The delicate link between protostellar environments and the emergence of conditions necessary for life has grown into a central theme of contemporary astrobiological research. Within protostellar disks, astronomers have now identified a remarkable diversity of organic molecules, from simple hydrocarbons and alcohols to complex prebiotic molecules, such as formamide, glycolaldehyde, and methyl isocyanate, molecular building blocks essential for the chemistry of life. Recent spectral studies from ALMA and JWST have confirmed that protostellar disks around young, sun-like stars contain abundant reservoirs of water ice, ammonia, carbon monoxide, and organic-rich compounds. These molecules are embedded in dust grains, forming icy mantles that serve as protective vessels for chemical reactions driven by UV radiation, cosmic rays, and thermal shocks. Over time, grains migrate inward toward warmer regions, triggering sublimation that enriches the disk's gas phase chemistry. Such chemical enrichment processes strongly suggest a universal pathway linking star formation directly to prebiotic chemistry. Laboratory experiments complement these astronomical observations. By replicating conditions found in protostellar disks, cold vacuum chambers irradiated by ultraviolet photons and energetic particles, scientists have demonstrated that surprisingly complex organic molecules spontaneously form on icy dust grain analogs. Such molecules include sugars, amino acids, nucleobase precursors, and amphiphilic compounds that could catalyze self-assembly and membrane formation, crucial steps toward cellular life. Thus, star formation environments inherently possess the ingredients required for life's molecular foundations, waiting only for the right planetary context to express their full potential. The migration and redistribution of these materials within disks further shape planetary habitability. Dynamical processes, such as radial drift and planet migration, redistribute volatile-rich materials across wide orbital ranges. This can result in rocky planets receiving deliveries of water and organics long after their initial formation. Recent isotopic analyses of Earth's water and volatile elements strongly suggest such processes occurred early in the solar system's history, likely seeded by protostellar disk dynamics and turbulent mixing. Protostellar outflows and jets, once viewed merely as mass loss mechanisms, are now understood to influence disk chemistry profoundly. The shocks they produce drive chemical reactions, forming complex organic molecules and inducing isotopic fractionation. These enriched molecular clouds subsequently re-enter protostellar disks, continually refreshing chemical complexity. Such feedback loops indicate that stellar birth and chemical evolution operate in an intricate dance, each influencing the other across astronomical timescales. At a larger scale, comparative studies of exoplanetary systems reveal the wide diversity in planetary composition, atmospheres, and orbital dynamics, directly shaped by the initial protostellar environment. Hot Jupiters, water-rich sub-Neptunes, and terrestrial worlds orbiting in compact, resonant systems illustrate outcomes determined by initial disk conditions. Through this comparative lens, protostellar research directly informs our understanding of the probability and diversity of habitable worlds across the galaxy. Astrochemical modeling efforts increasingly integrate detailed chemical networks with sophisticated fluid dynamic simulations, enabling predictions of how and where complex molecules form. These predictive tools not only interpret current observations but guide future explorations. For instance, they help target observations of molecules considered critical markers for prebiotic chemistry in distant, young planetary systems. Such observations are within reach of JWST and next-generation telescopes, transforming theoretical predictions into empirical discoveries. Ultimately, protostellar science holds profound philosophical implications. By tracing our biochemical origins back to these stellar nurseries, we are led to the realization that life's essential ingredients were not unique or exceptional. They were common, dispersed across countless protostellar disks throughout cosmic history. The profound implication is clear. Life's potential is woven into the fundamental processes of star and planet formation itself. The intricate relationship between protostellar environments and life's biochemical precursors deepens when considering cosmic radiation and stellar activity. Young protostars often exhibit intense magnetic activity, producing energetic flares and ultraviolet bursts that significantly alter the chemistry of surrounding disk material. While at first glance hostile, these high-energy events actually catalyze critical molecular reactions that might otherwise proceed too slowly to form biologically relevant molecules. Such stellar irradiation thus paradoxically enhances chemical complexity, contributing directly to the formation of prebiotic molecular reservoirs. One particularly intriguing phenomenon is the impact of cosmic rays, highly energetic particles originating from supernova explosions and energetic stellar winds, that continuously bombard protostellar disks. Cosmic rays penetrate deeply into dense molecular clouds and circumstellar disks, breaking molecular bonds and producing a cascade of reactive radicals and ions. These species rapidly recombine, giving rise to complex organic molecules such as amino acids, aldehydes, and nitriles. Laboratory experiments confirm that cosmic ray analogs can generate amino acids in icy analogs of protostellar grains, implying cosmic rays might have directly contributed to life's initial chemical toolkit. Protostellar magnetic fields also profoundly shape the early planetary environment. Observational studies using polarization-sensitive instruments reveal that dust grains within disks often align along magnetic field lines, providing clear observational signatures of these fields. Magnetically driven turbulence regulates disk accretion rates and dust grain dynamics, influencing planetesimal formation efficiency and chemical transport. Magnetic reconnection events can trigger sudden bursts of brightness and energetic particle acceleration, stimulating complex chemical reactions deep within the disk, ultimately enriching the planetary building blocks. Additionally, observations have shown that protostellar outflows entrain not only gas and dust, but also complex molecules, ejecting them far beyond the protostar's immediate environment. This molecular transport effectively seeds nearby star-forming regions, propagating chemically enriched material through stellar nurseries and potentially enhancing prebiotic chemistry in neighboring systems. The concept of protostellar ecosystems thus emerges. Individual protostars may chemically communicate across parsec-scale distances, collectively contributing to a galactic-scale chemical evolution. Emerging theoretical models now explore the potential connection between protostellar chemistry and planetary atmospheres. The chemical fingerprints acquired during a planet's early formation stages might persist within its atmosphere and interior throughout geological time. Consequently, protostellar disk chemistry could help explain the variety observed among exoplanetary atmospheres, some rich in carbon dioxide or methane, others dominated by hydrogen, nitrogen, or water vapor. These atmospheres ultimately determine planetary climate stability, habitability, and the likelihood of biological emergence. The search for biosignatures in exoplanetary systems increasingly intersects with protostellar research. Astronomers are developing observational strategies to trace molecules considered vital precursors to life directly within protostellar disks. Detecting such molecules across diverse protostellar systems could provide a statistical framework for understanding life's prevalence in the galaxy, thus anchoring astrobiological hypotheses firmly within empirical science. At an even broader level, protostellar research contributes insights into one of cosmology's fundamental questions. How common is life in the universe? The presence of abundant prebiotic compounds across protostellar environments implies that the raw ingredients for life exist everywhere star formation occurs. If the molecular precursors for life are ubiquitous, the formation of habitable worlds and potentially life itself might be routine rather than rare events in cosmic history. Future telescopes, including ESA's Ariel mission, NASA's Origin Space Telescope, and the next-generation ground-based Extremely Large Telescopes, ELTs, will probe protostellar disks at unprecedented resolution and sensitivity. These observatories promise to reveal chemical and physical processes with exquisite detail, allowing astronomers to directly test and refine models of planet formation, chemical complexity, and potential habitability. This new era will not only sharpen our understanding of star and planet formation, but could bring humanity significantly closer to answering the enduring question of whether life is a cosmic inevitability. Advances in computational astrophysics now enable astronomers to simulate protostellar and planet-forming environments with remarkable detail, encompassing scales from microscopic dust grains to entire stellar clusters. These simulations, informed by observations, integrate gravity, magnetohydrodynamics, radiation transfer, and complex astrochemical reactions to paint realistic pictures of early stellar nurseries. High-performance supercomputers generate virtual protostellar disks and clusters, allowing scientists to probe questions unreachable by current observational technology, such as how quickly Earth-like planets form, or how common prebiotic chemistry is across the universe. Recent simulations reveal how dust grains within disks undergo intricate growth pathways. Dust evolution begins with tiny interstellar particles, micrometers in size, which collide gently in low-velocity regimes, sticking together electrostatically to form porous aggregates. As these aggregates drift inward, they encounter increasingly turbulent regions, experiencing collisions that either promote growth or lead to fragmentation. This dynamic equilibrium determines the availability of planet-building material and shapes planetesimal formation processes, thus directly influencing the diversity and distribution of future planetary systems. One particularly compelling scientific frontier involves the direct imaging of protostellar disks in polarized infrared and millimeter wavelengths. Polarization observations reveal grain-size distributions, magnetic field orientations, and scattering properties, thus providing crucial insights into disk structure and evolution. For instance, recent polarimetric imaging from ALMA and Subaru telescopes has shown that young protostellar disks exhibit polarization patterns that indicate grain alignment by radiation or magnetic fields, offering tangible evidence of the interplay between magnetic fields and planetary formation. The discovery of protoplanetary disks in extreme environments, such as around protostars near massive black holes or within crowded star clusters, further expands our understanding of planet formation processes. Studies suggest that disks near supermassive black holes or within dense stellar clusters experience dramatically different irradiation levels, gravitational interactions, and dynamical perturbations compared to more isolated environments like our sun's birthplace. Remarkably, planets formed under these exotic conditions might differ greatly in composition, stability, and potential habitability. Protostellar populations themselves also inform broader astrophysical models. The distribution of stellar masses, called the initial mass function (IMF), is fundamental for understanding galaxy evolution, stellar population synthesis, and even the cosmic history of element production. Recent observational studies hint that the IMF might vary with environment, density, and metallicity of the star-forming clouds, suggesting star formation is more context-dependent than previously recognized. Thus, insights from detailed protostellar observations not only illuminate stellar and planetary origins, but also have implications for cosmological theories of galaxy assembly. Additionally, protostars serve as testing grounds for fundamental physics. The interplay of gravity, magnetism, and turbulence within disks provides natural laboratories for studying plasma instabilities, turbulent scaling laws, and magnetized fluid dynamics. These physical insights have cross-disciplinary impacts, influencing fields such as fusion research, atmospheric physics, and even Earth's oceanography, where turbulence and magnetic fields play similar roles. Recent astrobiological hypotheses also explore whether protostellar disks themselves might serve as transient habitats. Although life as we know it would struggle to develop in such extreme, radiation-rich environments, some researchers speculate that complex, self-organizing chemical systems, precursors to life, could temporarily form and exist within sheltered pockets in disk interiors. Studying these hypothetical transient chemical ecosystems challenges our notions of habitability and offers novel perspectives on the origins of life, suggesting that biological precursors might arise long before planets solidify and stabilize. The evolution of protostellar clusters introduces another fascinating research angle. Stars rarely form in isolation. Instead, they typically emerge within clusters containing dozens to thousands of protostars. Within these crowded environments, gravitational interactions dynamically sculpt planetary systems, eject stars, and redistribute planetary building material. Cluster dynamics influence planet survival rates, orbital architectures, and the frequency of rogue planets, worlds that wander freely through interstellar space without a host star. Understanding these phenomena sheds light on the diversity and stability of planetary systems throughout the galaxy. Ultimately, modern protostellar science fuses observational astronomy, theoretical physics, chemistry, and astrobiology into a coherent narrative. As telescopes continue to sharpen our view and computational models grow ever more sophisticated, humanity moves closer to grasping the profound connections that bind stellar birth, planetary genesis, chemical complexity, and the emergence of life itself. Protostars remind us that our existence is not a mere cosmic accident, but rather the elegant outcome of universal physical processes, patiently unfolding across billions of years in clouds of interstellar dust and gas. Another rapidly developing area in protostellar research involves the radiative feedback from young stars and its influence on both disk evolution and the broader star-forming environment. As protostars contract and approach the main sequence, they emit increasing levels of ultraviolet, UV, and X-ray radiation. These high-energy photons interact with the disk material and surrounding molecular cloud, heating the gas, ionizing atoms, and driving photochemical reactions. This radiation can photoevaporate the outer layers of disks, gradually dispersing gas and limiting the time available for giant planet formation. Observations from the Chandra X-ray Observatory and XMM Newton have revealed intense X-ray flaring activity in many T-Tauri stars, young, still accreting solar analogs. These flares are thought to arise from powerful magnetic reconnection events and contribute significantly to disk ionization. Enhanced ionization boosts the coupling between magnetic fields and disk material, facilitating magnetorotational instability and turbulence, which are essential for angular momentum transport and sustained accretion. However, strong radiation also accelerates the chemical evolution of the disk surface, affecting the retention of volatile compounds like water and organics, with long-term implications for planetary atmospheres and potential biospheres. In rich stellar clusters, external feedback from massive O-type stars becomes dominant. These stars produce intense UV radiation fields that can erode nearby protoplanetary disks through external photoevaporation. The Orion Nebula, for example, hosts dozens of such irradiated disks, known as proplets. Imaging from the Hubble Space Telescope has captured these fragile systems surrounded by ionized gas streamers, visibly eroded by their environment. Despite this harsh treatment, many of these disks still retain enough mass to form planets, highlighting the resilience of planet-forming environments even in extreme conditions. Another exciting frontier lies in disk substructures and planet formation diagnostics. ALMA has provided revolutionary high-resolution images of disks like HL Tau, TW Hydri, and AS209, revealing concentric rings, spiral arms, asymmetries, and shadows. These features suggest the presence of embedded planets or instabilities within the disk. The morphology of these structures allows astronomers to estimate the masses and locations of unseen protoplanets, offering a window into the earliest stages of planetary system assembly, while planets are still forming within the dusty cradle of their protostar. Complementary to ALMA, JWST now explores the infrared spectral fingerprints of ices and organics in protostellar disks. Its exquisite sensitivity enables the detection of frozen water, methane, carbon dioxide, and complex carbon-bearing molecules across the disk midplane, the potential feeding zones of terrestrial planets. Spectral maps also reveal temperature gradients and chemical transitions, showing where ice lines or snow lines occur, boundaries where volatiles condense from gas to solid. These lines define zones where different types of planets form and where volatile delivery to inner, rocky planets can occur. Meanwhile, isotopic fractionation studies offer a new diagnostic for early disk chemistry. Ratios such as D/H, deuterium to hydrogen, or superscript 1n/superscript 1n, nitrogen isotopes, vary depending on the physical and chemical conditions in which ice is formed. Comparing these ratios across different protostellar disks, meteorites, and cometary materials allows researchers to trace the evolutionary history of the solar system's own disk and compare it to planetary systems forming today. On the theoretical side, increasingly sophisticated simulations now couple dust dynamics and gas thermochemistry in evolving disks. These models track the radial drift of grains, the formation of pressure bumps, and the coagulation of particles into planetesimals, all while accounting for the chemistry of evolving ices and gases. By matching these simulations with observations, astronomers can test scenarios of planet formation, how Earth-sized rocky worlds or gas giants like Jupiter and Saturn emerge under different disk conditions. Finally, research into protostellar multiplicity reveals that a significant fraction of stars form not alone, but in binary or multiple systems. The gravitational dynamics of these systems can truncate disks, induce eccentric or warp structures, and dramatically alter the pathways of planet formation. In some cases, misaligned disks or inclined binaries may give rise to exotic systems with tilted planets or circumbinary configurations. Understanding how protostars evolve in these complex gravitational settings is crucial for interpreting the vast diversity of exoplanetary architectures now being discovered. Among the most compelling areas in the study of protostellar evolution is the transition from protostar to pre-main sequence (PMS) star, a phase that marks the shift from a heavily accreting, deeply embedded object to a fully revealed young star with a clearing circumstellar disk. This evolutionary milestone is critical for setting the final stellar mass, the disk's remaining lifetime, and the architecture of the eventual planetary system. As accretion from the envelope slows and the infall rate drops, the protostar enters what is observationally classified as the Class II phase. At this point, the star is visible at optical and near-infrared wavelengths, and its spectrum is dominated by photospheric emission rather than accretion luminosity. Yet, even as the star appears more stable, complex processes continue. Magnetospheric accretion, chromospheric activity, and episodic outbursts all define this transitional period. One of the most intriguing phenomena during the pre-main sequence phase is the occurrence of episodic accretion events, as seen in Fu Orionis and EX Lupi stars. These young stars undergo dramatic increases in brightness, sometimes by over 5 magnitudes, triggered by a sudden surge in disk accretion. These bursts can last for years or even decades, and their origin is still under active investigation. Possible triggers include disk gravitational instabilities, thermal viscous instabilities, or the migration of clumps within the disk toward the star. Such events may be crucial in regulating stellar mass growth and influencing disk chemistry, potentially resetting the thermal and chemical environment for planet formation. Simultaneously, disk winds and photoevaporative flows begin to play a dominant role in dispersing the circumstellar disk. Observations show that as accretion wanes, ionizing radiation from the central star, and sometimes external sources, heats the upper disk layers, launching a slow but persistent wind that removes mass from the system. Disk clearing progresses from the inside out, often leaving behind transitional disks with inner holes or gaps. These structures are particularly fascinating, as they may either indicate disk dispersal in progress or the presence of young, embedded planets that are dynamically carving the material. Studies of transitional disks have become a vital probe of planet-disk interactions. ALMA observations frequently reveal multiple rings and gaps, which, in conjunction with hydrodynamical simulations, provide indirect evidence for forming planets. These young systems offer a rare snapshot of planetary assembly and migration in action. Notably, the presence of asymmetries or vortices within transitional disks hints at the trapping of dust and gas, promoting rapid core growth, a possible solution to the timescale problem of forming gas giants before the gas dissipates. The final dissipation of the protoplanetary disk typically occurs over timescales of 3 to 10 million years, although variation exists depending on stellar mass and environment. Once the disk is gone, the star becomes a Class III object or weak-line T-Tauri star, in the case of solar-type stars, now largely isolated from its formation envelope and disk. At this stage, the star continues to contract along the Hayashi track for low-mass stars, or Henny track for intermediate-mass stars, radiating away gravitational energy until hydrostatic and thermal equilibrium are achieved, marking its arrival on the main sequence. Meanwhile, any planets that formed must stabilize their orbits in a disk-free environment, often undergoing dynamical rearrangements. The architecture of the mature planetary system is, in part, a fossil record of the disk structure, the migration history of planets, and the mass accretion history of the host star. Research into the end stages of protostellar evolution also overlaps with studies of stellar angular momentum evolution. Young stars are born rotating rapidly, but disk locking and magnetically driven winds efficiently remove angular momentum, preventing the stars from spinning apart. This interplay between magnetic braking, accretion, and contraction helps define the rotational velocity distribution observed in young open clusters, a key constraint for stellar evolution models. Crucially, the chemical memory of the protostellar phase may persist in planetary compositions. Studies of primitive meteorites, cometary ices, and interplanetary dust particles suggest that some materials accreted onto planets preserve isotopic and molecular signatures inherited from the early disk and envelope. These cosmochemical fingerprints provide a tangible link between present-day planetary bodies and the physics and chemistry of their protostellar origins. In summary, the final stages of protostellar evolution are not merely a tapering off of activity but a critical window in which mass, chemistry, angular momentum, and planetary architecture are finalized. The complex orchestration of accretion, outflow, radiation, and dynamical clearing defines the transition from a chaotic molecular collapse to the ordered structure of a planetary system. The journey from a silent cloud of dust to a luminous star with a retinue of planets is one of the most intricate and awe-inspiring processes in the cosmos. It is a saga of collapse and ignition, of chaos shaped by physics into coherence, of molecules organizing into worlds. From the first whisper of gravity in a dark molecular cloud to the final clearing of the protoplanetary disk, the protostellar phase encapsulates the fundamental forces that give rise to stars, planets, and the potential for life. In every protostar lies the echo of creation, a balance between destruction and formation, between radiation and accretion, between turbulence and order. It is here, in these hidden stellar cradles, that the architecture of future planetary systems is forged, where organic chemistry awakens, and where the seeds of habitable worlds are sown. As telescopes grow sharper and simulations grow deeper, humanity stands at the edge of a profound realization. The processes that gave birth to our sun and earth are neither unique nor rare. They are universal, unfolding across the galaxy and beyond. To study protostars is not merely to understand stellar evolution. It is to trace the blueprint of existence itself, to glimpse the quiet forges where matter becomes light, and where the long story of life may begin. And so, in the darkness of collapsing clouds, lit faintly by the glow of forming stars, we find the first sparks of cosmic destiny. For every protostar is a promise, not just of light, but of worlds, of chemistry, of memory, and perhaps, in time, of consciousness.
In the silent reaches of the cosmos, far beyond the familiar swirl of our Milky Way, lies a giant whose very presence challenges the boundaries of galactic formation, UGC 2885. Nicknamed the Godzilla Galaxy, this leviathan sprawls across over 800,000 light-years, its spiral arms extending with grace and mass that dwarf our own galactic home. With a stellar mass estimated at more than 10 times that of the Milky Way, UGC 2885 is not merely large, it is a colossus that provokes fundamental questions about the mechanics of galaxy growth. Despite its gargantuan size, UGC 2885 exhibits an unusual serenity. It lacks the chaotic scars of recent mergers or violent interactions often associated with galactic expansion. Its structure is symmetrical, its rotation smooth, its spiral arms well-defined and orderly. Such calmness, paired with its scale, suggests a prolonged, undisturbed accumulation of gas and stars, a slow, almost contemplative evolution that contrasts with the more tumultuous histories of other massive galaxies. This observational portrait hints at an alternate pathway in the evolution of large disk galaxies, one that favors isolation and steady accretion over collisions and cannibalism. It raises the possibility that certain environments in the universe, cosmic suburbs rather than bustling clusters, permit galaxies to quietly reach extremes of mass and size without destabilizing their disk structure. UGC 2885 may have spent billions of years sipping rather than gulping intergalactic gas, gradually fueling star formation while maintaining balance. The galaxy's extended disk is still actively forming stars, albeit at a moderate rate. This low-efficiency star formation is particularly striking given its vast reservoirs of hydrogen gas. It suggests a regime where gravity, angular momentum, and gas dynamics are delicately balanced, permitting growth without triggering starbursts or morphological disruptions. The galaxy is enormous, yet measured in its energy output, a gentle giant whose scale is matched by its restraint. UGC 2885 becomes a cosmic laboratory for probing the limits of disk galaxy formation. How much mass can a spiral galaxy accumulate before instability sets in? What roles do dark matter halos, angular momentum conservation, and environmental isolation play in sustaining such a vast rotating disk? The answers lie in observations that blend radio maps of hydrogen distribution, optical studies of stellar populations, and simulations that push models to the extremes of their parameters. The detailed mapping of UGC 2885's neutral hydrogen has revealed a massive, extended reservoir that stretches well beyond its stellar disk. This immense supply of gas not only acts as raw material for future star formation but also serves as a tracer for the galaxy's gravitational potential. Its rotation curve remains flat and extended, a signature that dark matter plays a significant role in maintaining the galaxy's stability across such vast scales. The inferred dark matter halo is colossal, one of the most massive associated with a disk galaxy, yet its distribution must be finely tuned to allow the disk to remain thin and ordered. Spectroscopic studies across the disk show a surprisingly uniform metallicity gradient, with only a gentle decline from the center to the outskirts. This suggests that UGC 2885 has not experienced major mergers or disruptive inflows, which would typically stir up the chemical distribution. Instead, a gradual enrichment process seems to dominate, powered by generations of steady star formation recycling material into the interstellar medium. Such chemical regularity hints at a deep equilibrium state, where the galaxy evolves under self-regulating processes. Deep field imaging and high-resolution photometry have failed to uncover tidal streams or stellar substructures that would indicate recent accretion events. This absence of fossil signatures supports the hypothesis that UGC 2885 has followed a path of relative isolation. Its environment is unusually quiet, residing in a low-density region where major interactions are rare. This cosmic solitude could be the key ingredient that allowed such a giant to form and remain undisturbed for billions of years. Computer simulations that attempt to replicate UGC 2885's properties are still grappling with the challenge of reproducing its enormous mass without inducing bar instabilities, disk warping, or morphological transformation into a lenticular or elliptical structure. Theoretical models must account for the complex interplay between cooling gas, feedback from stellar winds and supernovae, angular momentum transport, and the influence of dark matter halos. UGC 2885 thus becomes a testbed for refining models of galaxy evolution, particularly in the high-mass, high-angular momentum regime. Its existence also challenges the empirical scaling relations that define the galaxy population, such as the Tully-Fisher relation, which links rotational velocity to luminosity. UGC 2885 sits at the extreme high end of these relations, and its outlier status offers a valuable data point to probe the limits of these correlations and their physical underpinnings. Precision measurements of its kinematics help recalibrate these relationships and offer insight into the universality, or flexibility, of galactic laws. Yet perhaps the most intriguing aspect of UGC 2885 is not simply its scale, but the quiet mystery of its success. How, in a universe where gravity so often conspires toward chaos, shattering galaxies in collisions, triggering starbursts, feeding violent black holes, did this spiral giant survive and thrive with such grace? There is no evidence of a central active galactic nucleus, no quasar-like blaze from a feeding supermassive black hole. Its core is subdued, its heart seemingly asleep. This silence raises a profound question: Did UGC 2885 ever ignite with the fury of an active nucleus, or has it always existed as a gentle colossus, avoiding the violent feedback that typically quenches star formation in massive galaxies? If so, it suggests a possible divergence in the evolutionary fate of galactic giants, between those that awaken their central monsters and those that remain in quiet slumber. Moreover, its angular momentum is remarkably well preserved. In most massive galaxies, interactions, mergers, and internal torques tend to redistribute angular momentum, thickening the disk and fostering bulge formation. Yet UGC 2885 retains a clean, extended disk with minimal bulge growth, an architectural marvel that seems to defy the statistical trends. Could this be a glimpse of what the Milky Way might become in a far future era, if left alone to evolve in peace? Simulations of isolated halos with high spin parameters have begun to hint at the conditions necessary to build such a structure. These rare halos, rotating with just the right amount of angular momentum, can stabilize enormous disks without collapsing inward. The baryonic matter cools slowly, settling into elegant spirals instead of fragmenting into clumps. In this context, UGC 2885 might not be an anomaly, but a beacon, a rare but natural endpoint for certain initial conditions set in the early universe. What remains unknown is how such a galaxy maintained this delicate trajectory for over 10 billion years. Cosmic time is unforgiving. Galaxies are born into turbulence, bombarded by satellites, swept by filaments of inflowing gas, caught in gravitational eddies and flows. For UGC 2885 to emerge unscathed, massive, ordered, and rotationally supported, implies a remarkable convergence of luck and physics. Or perhaps, a rule yet unrecognized, a pattern overlooked in the chaos. And then there's the question of what comes next. Will UGC 2885 continue this calm expansion indefinitely, or are we witnessing it in a rare, transitional phase? Could it be on the cusp of awakening, its central black hole slowly stirring, the equilibrium beginning to tilt? Is there a vast inflow of gas gathering in the outskirts, soon to trigger a new epoch of star formation, or a collapse into central activity? Or has it already passed its golden age, now gliding quietly into senescence, its vast arms like the fading ripples of a once mighty wave? In every pixel of its image, in every data point of its spectrum, UGC 2885 whispers of an untold galactic biography. Its size is not just a matter of measurement, it is a challenge to theory, a monument to cosmic patience, and perhaps a hint at how the universe can build giants not with fire and fury, but with silence and time. Astronomers now look at UGC 2885 not merely as a subject of classification, but as a cosmic relic, one that may hold the keys to understanding the upper limits of disk galaxy formation. In a universe where most spirals are modest, and giants are often disordered or transformed into ellipticals, UGC 2885 stands as a contradiction, a massive spiral that retained its identity, seemingly untouched by the violence that defines cosmic evolution. Deep radio surveys continue to probe its cold gas halo, revealing an envelope so vast it challenges the very definition of the galactic boundary. Some estimates suggest its hydrogen halo extends well beyond the optical disk, possibly over 1 million light-years across, blurring the line between galaxy and intergalactic medium. This immense reservoir acts not only as a fuel tank for future star formation, but also as a shield, slowing the accretion of external material and buffering the galaxy against disruptive gravitational events. High-precision photometry has begun to resolve stellar populations across its disk, uncovering subtle differences in age, metallicity, and kinematics. The inner regions reveal older, redder stars, remnants of an early epoch of rapid star formation, while the outer arms display younger, bluer populations, still in the act of forming from pristine hydrogen. This radial gradient tells a story of inside-out growth, where the galaxy expanded like a ripple in still water, slowly accumulating mass over cosmic time without ever losing its symmetry. And still, questions multiply. Why is its star formation efficiency so low, given the abundance of gas? Are magnetic fields playing a stronger role than expected, stabilizing the disk against collapse. Could UGC 2885 be part of a new class of ultramassive, low-activity spirals, cosmic hibernators that hoard their fuel rather than burning it in starbursts? Or is it simply an outlier, a galactic anomaly born from initial conditions so rare that we may never observe another like it? Telescopes like JWST and future observatories promise to peel back even more layers. With deeper infrared imaging, astronomers hope to trace the faintest stellar structures in its outskirts, looking for warps, flares, or low-density tidal streams that may hint at past interactions invisible in current data. Spectroscopy at unprecedented resolution may uncover the subtle fingerprints of past mergers, buried deep in the orbits of stars or the metallicity of star clusters. Gravitational lensing studies could help refine its dark matter profile, testing whether its halo is indeed the unusually massive, smooth, and extended structure that current models predict. And beneath it all, the gravitational hum of its unseen heart, likely a supermassive black hole, remains quiet. Not dormant, but patient. Waiting. There is something almost eerie in that stillness. In a galaxy so grand, so massive, so richly supplied with gas, we might expect chaos. But UGC 2885 offers another vision, that the universe, under rare and precise conditions, can sculpt order from abundance. That growth need not be violent. That a giant can rise not through conquest, but through harmony. Perhaps, then, UGC 2885 is not just a record of what galaxies can become, it is a vision of what they might have been, had the cosmos chosen a quieter path. Such reflections cast UGC 2885 not only as an astrophysical subject, but as a philosophical one, a quiet sentinel in the dark, defying the odds, bending the expected arc of galactic destiny. While the cosmos is often viewed through the lens of violence, supernovae, mergers, jets, and black hole eruptions, this galaxy invites another narrative, one of persistence, balance, and sublime restraint. Its spiral arms, vast and unwound, rotate in almost hypnotic stability, as if tracing invisible pathways written by the early universe. These arms, extending over 400,000 light-years from the core, may act as cosmic memory, echoes of tidal rhythms, density waves that have gently moved outward for eons, organizing matter into stellar generations. Within them, star formation proceeds with measured calm, lacking the bursts and turbulence found in smaller, more chaotic systems. Here, stars are born not in firestorms but in quiet nurseries, embedded within vast molecular clouds that drift lazily through the disk. The efficiency is low, the pace deliberate, as if the galaxy has all the time in the universe. And perhaps it does. Because UGC 2885 is not consuming itself in youthful exuberance, it is pacing itself, conserving fuel for a longer story. Some researchers speculate that this galaxy could serve as a bridge in our understanding of cosmic transition, from youthful, active spiral galaxies to mature, passive systems. Most massive galaxies eventually lose their disks, forming bulges and halos through mergers. But UGC 2885 remains intact. It hints at the possibility of a spiral aging with dignity, never collapsing into chaos or transforming into an elliptical relic. Could it represent an evolutionary fork? One where galaxies, under certain cosmic alignments, avoid both starburst burnout and merger-driven collapse. In this scenario, UGC 2885 is not an accident, but an alternate conclusion, a whisper of what galactic evolution might be in a universe governed by delicacy as much as destruction. It is possible that the galaxy's size protects it. Its vastness creates a kind of internal inertia, buffering against disruptive feedback loops that plague smaller systems. Stellar winds and supernovae, which can destabilize dwarf galaxies or trigger runaway bursts in mid-size spirals, dissipate harmlessly within the enormous volume of UGC 2885. Energy spreads thin. Turbulence fades before it can spread. Gravity reasserts order. Even more fascinating are the implications for galactic habitability. A galaxy like UGC 2885, with its long periods of calm, slow-burning stars, and wide buffer zones away from active nuclei, may offer extraordinary potential for life. If intelligent civilizations were to arise in its outer arms, they might gaze inward upon their galaxy's grandeur and find it stable, predictable, almost serenely eternal. A cosmic cradle where time moves slowly, and danger sleeps. And so UGC 2885 becomes more than an astrophysical curiosity. It becomes a symbol of potential, a vision of longevity, peace, and silent strength in a universe often defined by the opposite. It reminds us that the cosmos is vast enough to allow exceptions, and rich enough to craft structures that are not just functional, but majestic. But this tale may not be over. Observations continue, ever deeper, ever finer. Each photon collected from this spiral giant may carry a clue. Somewhere within those quiet arms or that vast, gas-rich halo may lie the final answer to how such a giant was born, and whether it is truly alone in its kind. Or perhaps, scattered across the darkness, there are other titans still hidden. Other Godzilla galaxies waiting to be seen. The search for such titans has now become a quiet obsession among astronomers, an unspoken hope that UGC 2885 is not a lone outlier, but rather the first visible peak of a hidden population of ultramassive, undisturbed spirals. If they exist, they are rare, lurking in the underexplored outskirts of the cosmic web, far from the bustling centers of galactic clusters. Their isolation would be both their birthplace and their shield, allowing them to grow without disruption. Future sky surveys, deep, wide, and multi-wavelength, may reveal their presence. Instruments like the Vera C. Rubin Observatory will map the faintest structures in the night sky with unprecedented sensitivity, capable of detecting ghostly disks, sprawling hydrogen halos, and subtle spiral arms that current surveys miss. The James Webb Space Telescope, peering into the infrared, may glimpse their ancient stars and star-forming regions cloaked in dust. And radio arrays like the Square Kilometre Array will trace their cold gas skeletons across millions of light-years, outlining galactic giants by their invisible breath. But even as we prepare to detect their kin, UGC 2885 remains the benchmark, a solitary monument against which others will be measured. Every detail of its rotation curve, every fluctuation in its gas density, every metallicity gradient across its disk becomes part of a growing library of what may be possible. Not just astrophysically, but cosmologically. Because if galaxies like this are rare, they tell us something fundamental about the universe, that tranquility on such a scale is improbable. That order, when it appears in a sea of chaos, is not merely beautiful, it is meaningful. It reveals the tight constraints within which galaxies must evolve to reach such a state, and how narrow the window is between complexity and collapse. It forces theorists to refine their models, to tune simulations not just for violence and variety, but for elegance. To explain not only how galaxies burn bright and die, but how they endure. How angular momentum must be preserved, how star formation must be throttled, how black holes must be tamed. UGC 2885 becomes not just a test of physics, but of philosophy. Can the laws of the universe allow such perfection? Or was it a cosmic accident, unrepeatable and unplanned? Even its name, Godzilla Galaxy, feels paradoxical. Godzilla, the icon of destruction, now applied to a creature of cosmic harmony. But perhaps that's the deeper irony. In a universe filled with fire and collapse, perhaps survival is the most extraordinary act of all. And so UGC 2885 rotates on, alone but not forgotten. A spiral without scars. A giant without fury. A question without a final answer. Not yet. Not yet, because UGC 2885 continues to pull at the edges of our understanding, like gravity itself bending the straight lines of theory. With every observation, it reminds us that the universe is not only governed by destruction, but by patience. That in the grand contest between chaos and order, there are places, rare, hidden, enormous, where order has quietly won. And still, its mass is not its only mystery. The rate at which it spins, the smoothness of its disk, the unexpected coldness of its gas, all suggest a hidden orchestration, as if the galaxy has maintained a delicate internal equilibrium for billions of years. Gravity pulls inward, pressure pushes outward, rotation balances the two. But on this scale, hundreds of thousands of light-years, the stability defies not just observation, but expectation. Some speculate about ancient events that may have set UGC 2885 on this quiet trajectory. Was it born in a region of the early universe with unusually low density, allowing it to evolve in near-total solitude? Did it receive a cosmic inheritance, a particularly massive dark matter halo with just the right spin, shielding it from galactic predators and giving it room to breathe? Did it once have siblings, now consumed or dispersed, leaving it as the last survivor of a long-lost filament? Or is it older than we think, not in age, but in cosmic maturity? Could UGC 2885 represent a kind of accelerated galactic evolution, where the usual timescales of star formation and disk growth unfolded faster, more cleanly, more efficiently, then slowed again, allowing the structure to crystallize in place? A galaxy that grew not through disruption, but through discipline. It might even offer insights into the deep interplay between baryonic matter and dark matter, the strange, unseen scaffolding that shapes galaxies from behind a cosmic veil. UGC 2885's halo may be unusually smooth, unusually spherical, unusually cold. Perhaps its very existence hints at variations in the dark sector, new physics yet to be found, written not in particle collisions, but in the slow dance of spiral arms across a million light-years. Even now, long after it formed, UGC 2885 remains astonishingly quiet. It emits no gravitational waves, no bursts of X-ray radiation, no signs of recent upheaval. It does not rage, it endures. And that endurance may become its legacy. For while most galaxies live brief, brilliant lives, flaring with activity, then fading, UGC 2885 seems designed for the long game. It may continue rotating calmly for trillions of years, forming stars slowly, fading gently, drifting farther from the rest of the universe as dark energy stretches space. Long after the last quasar dies, long after the spiral arms of the Milky Way blur into a spheroid, UGC 2885 may still be there, dimmer, quieter, colder, but intact. A fossil of harmony. A relic of balance. A monument to what the cosmos can build when it chooses not war, but wisdom. And in that distant future, when the stars of younger galaxies have long since burned out, when interstellar gas has been consumed or dispersed, and when the universe itself has grown vast and empty, UGC 2885 may remain a lighthouse in the dark, its spiral arms faded, its starbirth slowed to a whisper, but its structure still recognizable, still whole. Imagine such a time, trillions of years from now, in an era of cosmic silence, where galaxies have merged into red ellipsoids or evaporated into the void, and black holes dominate the landscape of space. Amid this dying universe, UGC 2885 may still quietly spin, like a great watch wound by some forgotten hand. The stars within its disk may cool to embers. Its gas may freeze into molecular clouds too diffuse to collapse. But its form, its beautiful, improbable spiral form, may persist like a memory the cosmos cannot quite erase. And if there is life, somewhere within it, perhaps clinging to a dim red dwarf in its outer rim, it may one day look inward, trying to make sense of the galaxy's enormity. Perhaps they will not remember the Milky Way or Andromeda or the clusters that once peppered the sky. But they will have this, a galaxy vast beyond comprehension, yet gentle enough to harbor stillness. A Godzilla not of destruction, but of survival. For now, though, we observe. We map. We simulate. We question. We study the gravitational shear in its halo, hoping to detect deviations from cold dark matter predictions. We analyze the scale length of its disk, comparing it to formation models across redshifts. We run simulations with high spin parameters and low merger rates, seeing if the algorithms can, even once, recreate what the universe sculpted naturally. And always, we return to the same astonishment: UGC 2885 should not exist in this form. But it does. And so it whispers, no, declares, that there are still exceptions in a universe of rules. Still islands of grace in oceans of entropy. It has become a kind of cosmic koan, massive, yet unbroken, ancient, yet star-forming, isolated, yet complete. A riddle etched across 800,000 light-years of starlight. And in that riddle lies possibility. Because if such a galaxy can exist once, perhaps it can exist again. Or already does, unseen. And if nature can assemble such grandeur not through violence, but through quiet coherence, perhaps our models are incomplete not in their equations, but in their assumptions. Perhaps we have underestimated what the cosmos can build when it chooses to be patient. UGC 2885 is a monument not only to astrophysics, but to all. To the notion that not all giants must roar. Some simply are. And in their being, they rewrite what we thought we knew. And perhaps this is the true legacy of UGC 2885, not merely a record breaker, not just a cosmic anomaly, but a challenge. A challenge to our understanding of how galaxies grow, of what the universe permits, and of what it prefers. For if the cosmos has an aesthetic, if it sometimes chooses symmetry over chaos, silence over spectacle, then UGC 2885 is its masterpiece. Its disk, unmarred by violence, is a canvas painted in slow motion. Each arm, stretched wide into the void, curves not just with gravity, but with purpose. Each star, whether ancient or newborn, plays its role in a choreography so vast that it escapes the imagination. And somewhere in its quiet heart, perhaps in the very stillness of its core, lies the echo of cosmic intent. There is poetry here, written in hydrogen and dust, in spin and silence. It is a kind of galactic haiku, enormous, elegant, enduring. And for scientists, it is a call to look deeper. To revisit assumptions long held. To imagine galactic formation not solely as a process of competition and collision, but as one of balance, where isolation, angular momentum, and environmental quietude can conspire to create not just survival, but splendor. UGC 2885 is a data point, yes, but it is also a meditation. It teaches us that the cosmos is more versatile than we imagine. That not all galaxies are forged in fire. That not all evolution is violent. That endurance itself may be a form of excellence. Even now, as astronomers train their eyes and instruments on newer, brighter discoveries, on quasars blazing from the dawn of time, on galaxies colliding in flashes of light, UGC 2885 continues its slow revolution. Not demanding attention. Not seeking glory. Simply being, perfectly, quietly, vastly. It rotates not just through space, but through wonder. It is not loud. It does not scream across epochs. But it stays. And in a universe where so much is transient, where light flickers and fades, that constancy may be the most powerful force of all. Because perhaps one day, long after our telescopes fall silent and our equations grow cold, UGC 2885 will still turn, an eternal spiral in a dimming sky. And someone, somewhere, may look up and ask the same question we do now. How could something so immense be so gentle? And in that question,